Welcome back. Let's continue talking about our related rates. If you recall, these are things that are changing where their rates are related to one another. For example, if you're holding a snowball in your hand and you bring it inside the house, it starts to melt. So not only is the radius of the sphere of the snowball changing and decreasing, but so is the surface area of your snowball as well as the volume of snow that makes up that sphere of that snowball. So remember the process we want to do. We want to draw a picture if possible, determine what we know, determine what we want to know, determine the given relationship between what we know and what we want to know, and then solve and be sure to answer our question. So let's pick up with another example. A 6-foot man walks at a rate of 5 feet per second away from a lamppost that is 15 feet tall. When he is 10 feet from the base of the lamppost, at what rate is the length of his shadow changing? So this is definitely one of those situations where we are probably going to want to draw a picture. So here we have a lamppost that's 15 feet tall, and we have a man that's 6 feet tall, and this man is walking away from the lamppost. Now the lamp shines a light down on him, which causes him to form a shadow in front of him. As he is walking away from the lamp, his shadow is also walking away from the lamp, if you will. All right, so what do we know? We know that dt is 5 feet per second. The rate at which he's walking away from the lamppost is 5 feet per second. We want to know ds dt, the rate at which the shadow is walking away from the lamppost, when the distance from the lamp is 10 feet. All right, so now we need to figure out how are these related. Now we can't use something like the Pythagorean theorem here because the base of this is unknown and the hypotenuse is unknown, so we can't use things like a squared plus b squared equals c squared. But what do you notice we have? We have this big right triangle here between the lamppost and the ground. We also have a right triangle inside there between the man and the ground. We have similar triangles. So let's take a look at those similar triangles. We have this big outer triangle, which is 15 feet tall here, and then its length is d, the distance the man is from the lamp, plus s. And then we have this one where the man is 6 feet tall, and the base of this triangle is just s, the length of the shadow. If you recall back from your geometry days, when you have similar triangles, they are proportional to one another, which means the proportion of this leg and this leg is the same as the proportion of this base and this base, which is the same as the proportion of this hypotenuse and this hypotenuse. So if you take the proportion 15 over 6, that's going to give you the same proportion as d plus s over s. So now we can cross multiply here, take this 15 times s and this 6 times d plus s. And we get that 15s is equal to 6d plus 6s. And if we just subtract 6s from both sides, our relationship is that 9 times s is equal to s times d. And I want to know at what rate is this all changing with respect to time. So I'll take the derivative with respect to time of both sides. The derivative of 9s with respect to t will be 9 ds dt. And the derivative of 6d with respect to t will be 6 dd dt. And we're looking for the rate at which the shadow is changing, so I'll divide both sides by 9, and I want to do this when I know that the rate at which the man is walking away from the lamppost was 5 feet per second. So when I do this out, I can see that the man's shadow is moving at a constant rate of about 10/3, which is about 3.3 feet per second. Let's do one more example. An empty rectangular reflecting pool is 10 feet wide, 50 feet long, and 2 feet deep, and it is being filled at a rate of 2 cubic feet per minute. How fast is the water level rising? So let's draw a picture. So we have this rectangular pool right here, where it's 10 feet wide, 50 feet long, and 2 feet tall. And we're pouring water into it. And as we're pouring water into it, the level of the water is rising. So this is changing all the way up to 2 feet, and then after 2 feet, it'll start spilling over. Now, the 10 feet isn't going to change, and the 50 feet isn't going to change. And if you think about when you're raising water, it raises at a nice level, but in a rectangle, it doesn't fill part of it and then go back and fill the other part. It's continually raising across that entire bottom rectangle there. So we know dV dt, the rate at which the volume is changing is with respect to time, is 2 cubic feet per minute. I want to know right here the height. At what rate is the height changing with respect to time, knowing that the most it can rise up to is 2 feet. After 2 feet, water will be spilling everywhere. Now keep in mind again that this 10 feet wide and this 50 feet long aren't going to change. So how are these all related? Well, the volume of a rectangular box is length times width times height. The height is constantly changing, but the width and the length are not. So we have that the volume is 10 feet times 50 feet times whatever the height is, which gives me 10 times 50 is 500, and feet times feet is feet squared. So remember those units, they're going to come back in, times whatever the height is. So the given equation, the given relationship we're working with is V is 500H. So I want to know the rate at which this is all changing with respect to time. So I'll differentiate both sides with respect to t. The derivative of V with respect to t will be 1 dV dt, and the derivative of 500H with respect to t will be 500 dH dt. And so I'm looking for dH dt, so I'll divide both sides by 500. Now remember the rate at which dV dt was changing. It was changing at a rate of 2 cubic feet per minute. And remember this 500 right here was 10 feet times 50 feet, which was 500 feet squared. So now this cubic feet and these square feet will reduce down to just 1 foot per minute. So dH dt is changing at a rate of 1 over 500 feet per minute. I apologize, that should be 1 over 250 feet per minute. And 1 divided by 250 is 0.04 feet per minute. So the water is rising at a level of 0.04 feet per minute. That's it for related rates. We'll see you next time.